So let's look at a particular example of a classical system, and that's going to be the ideal monatomic gas. Okay, so what is the monatomic gas? You know, it has only one atom, and it has no internal structure, and no interaction. Okay. So all it does is that it has some kinetic energy associated to it, and that is that complete Hamiltonian. So what is the partition function? For one atom of this gas, let's call the partition function Z1. So Z1 is going to be 1 over 2 pi h bar cubed, and then there's an integral over d cubed q d cubed p, and then we have e to the power minus beta p squared by 2m. Now we can take the gas to be enclosed in some box or container of volume V. Even if it is not there, you know, we just do that to regulate this integral. Then we can just do the q integral, and then we have V 2 pi h bar cubed, and then we have d cubed p, and then e to the power minus b p squared by 2m. Okay. So this now the next integral, these are it's a set of 3 Gaussian integrals, right? So let me remind you, the fundamental Gaussian integral is from minus infinity to plus infinity of e to the power minus a x squared. A is a positive real number, and when you integrate that, it gives you square root of pi over a. So here we use it 3 times for the 3 integral. And if I do that, then, you know, just 2 lines of algebra tells me that I get V, and then I get M kBT divided by 2 pi h bar squared 3/2, okay? Now, because the dimension of V is length cubed, it must be that this thing should also have the dimension of 1 over length cubed. So we write this as V divided by lambda cubed. Now, what is lambda? Lambda is nothing but 2 pi h bar squared divided by m kBT, the whole thing under a square root. Okay. Now, lambda has dimensions of length, and it's called the thermal de Bruy wavelength. And it can be thought of as the average wavelength of the particle at temperature T. And we'll see soon why. Or average de Bruy wavelength of the particle at temperature T. Now, some of you may not know what the de Broglie wavelength is, right? Is that correct? Is there anyone who doesn't know?
Yes, sir.
Okay. So let me just give you a brief introduction to what the de Broglie wavelength is. So it's a quantum quantity. Sorry?
So it's basically as far as I know, when a particle having a little a wave nature,
Right.
a particle having wave nature, we define it using the de Broglie wavelength.
Yeah. So it's a quantum mechanical concept. So the idea is that, Einstein posited that light has a particular particle nature, right? If, light is a particle, and he said that the energy of a particle light, which is now called photon, should have the energy h nu, where nu is the frequency, and that's if he express it in terms of h bar, it's h bar omega, where omega is the angular frequency. Now, what de Broglie said was that if electromagnetic waves can have a particle nature, what if small atomic particles could have a wave nature? Is that possible? And he explored that, and he proposed that the momentum of such a particle should be related to its its wavelength by h by lambda. Okay. And sorry, I should use a non-vector notation. Okay. And these two relationships are known as the de Bruy relationship, because for a quantum particle, Nusaiba is saying that she cannot get inside. Okay, let's see. Okay. Okay, let's see if I can get Nusaiba into the... okay, I'm going to ask her to try again. Okay. Right. So, so the idea was that, suppose you have a proton, traveling in this direction, as a quantum. So what de Broglie said was that there should be some sort of matter wave associated with this proton, with this particle, and so one of the phenomena that we associate with matter wave is diffraction, right? Interference, diffraction. So there should be these properties of waves should also be reflected in particle experiments. And then after de Broglie had suggested this, Davison and Germer, it's Davison and Germer, what they did is that they took a neutron beam and then they reflected it off a lattice of atoms. And the lattice of atoms acted like a diffraction grating. And the reflected beam, they exhibited the pattern that is typical of diffraction. And therefore, Davison and Germer experimentally proved that particles also have a wave nature. Okay? And as we can see is that the more energetic or more higher the momentum of the particle, right, the 1 over lambda is higher, so lambda is smaller. So if it's very energetic, it has very small wavelength. If it's less energetic, it has long wavelength. Okay. So that's the de Broglie wave. Now, what is happening here is that
Sir,
this particle, yes?
Does the de Broglie wavelength collapse when we go to a classical system like a tennis ball?
No, it doesn't. It just becomes extremely, extremely. Hang on. Let me be careful about that. It just becomes very, very, very small, the de Broglie wavelength.
Oh, okay.
Okay. So large that it's actually not physically measurable. In fact, I think there are some problems I can assign about that to, so that you can estimate the wavelength of those for a macroscopic object. Okay, so there's a lot in this story because there's uncertainty principle and all that, and I'm not going to unpack all of that today. But I wanted to just motivate that particle can have a de Broglie wavelength, and in a given temperature, this could be. We shall see that we can associate, because we are talking about the canonical ensemble, right? So therefore, there's going to be some average energy, and there's going to be some average momentum, and we can associate a wavelength with that average momentum, and that is going to be this de Broglie wavelength, okay? And we will see that shortly. And you can think of the partition function as, it's measuring the volume of your gas in terms of the Bruy wavelengths, okay? Now, so far we have seen the partition function only for one particle. Now let's look at n particles, right? Because we have multi-particle system. A gas is a multi-particle system. So in that case, the partition function is going to be, so this is Z1, this is going to be Zn. Now, if they're non-interacting, which is the case for a monatomic gas, then we saw that for independent systems, the partition function just multiply, right? Okay. Somebody wants to come in? Okay. So the partition function for the n particle system would be the partition function for the one particle raised to the power n. And then we should get v to the power n divided by lambda 3n. Okay. Now here we are assuming, for the time being, that the particles are distinguishable. If they're indistinguishable, then we are overcounting, and we have to divide this by 1 over factorial, well, multiply this by 1 over factorial n factorial, and that's something we will do in a short time. But for now, let's just look at this partition function.
Sir, wouldn't it be overcounting if they were indistinguishable?
Yes. And that is
I
the
think-
whole idea behind something called Gibbs paradox that we will come to later today. Okay.
I think I
Okay.
misheard.
So you're missing something? Is that what you're saying?
I think I misunderstood what you said. So
Okay. Yeah. So this is for particles that are distinguishable. You see, classical particles, even when they are the same particle, are distinguishable, right? If you have two billiard balls, you know that at every point in space, in time, they have well-defined position and momentum. Therefore, they're distinguishable. And the same goes with if gas molecules were classical, then they will also be distinguishable. But in quantum mechanics, they are indistinguishable. Now, what does that mean? That means that suppose you have a gas molecule here and a gas molecule here. So quantum mechanically, what it means that there is a wave function, a de Broglie wave, if you like, which is centered around this, so-called position of the molecule. In reality, the position of the molecule is not something that makes sense in quantum mechanically. So what we have here are two wave packets. So we can call this like particle number 1 and particle number 2. But suppose they are traveling towards each other, and at some point they merge. They overlap. And then after that, what happens is that, this particle, one particle is going in one way, another particle is going the other way. So this is 1 plus 2. Now I ask you the question, is this particle 1 or is this particle 2? Or is the other way around?
Sir,
What do you
are
think?
they distinguishable?
They're quantum particles.
yeah, we can't tell in this case.
No one knows.
We do know. Well, yeah, we don't know. You're right. Because they are actually indistinguishable. Classically, what can happen is that, they can go through each other, or they can like collide and go back, right? But classically, you would know the difference because you would be able to track the particles all the way through. But in quantum mechanics, there is no way of tracking it. But the fact that you might say, oh, this is something that we just don't know. It could be it's a 50-50% chance, right? But quantum mechanics says, no, that's not true. There is no meaningful way in which you can say this particle is going this way and this particle is going this way, or this particle is going this way, or this particle is going this way. Because the statistics of two distinguishable particles, be they described by some wave, and therefore you don't know what's happening, and two indistinguishable particles, where you cannot distinguish between these two things will give you experimentally different results. Okay?
Sir,
And you
if
can go and do experiments. And it turns out that in quantum mechanics, particles are fundamentally indistinguishable. And you get different kind of statistics. And that gives rise to, say, for integer spin particles, something called Bose-Einstein statistics. Where Bose is Schuttenbusch from Dhaka University. And, if they're fermions, they're called Fermi-Dirac statistics. Fermi-Dirac, sorry. And in 2+1 dimension, you can have objects which are called anyons, and anyons can have anyonic statistics, okay? So anyway, somebody had a question, I think.
Yes, sir. If the particle 1 and 2 are both electron, we can say that they repelled each other. So we know that the 2 particle is going the opposite way and the 1 particle is going the other way after repelling.
Well, they don't have to repel each other because they're you know, and you know, this can happen in higher dimensions, right? So they can miss each other. Like, what if one electron is coming like this, another one is coming like this, and you know, and they go like this, but you know, there is enough of a like you know, so this is the how much the wave function is spread. So you know what happened, which one went left, which one went right, you don't know. Okay.
Okay.
Yeah, the interesting thing is that you can actually, you know, predict the prediction of distinguishable particles and indistinguishable particles are different. Okay, so at some point I will give you, well, you will learn about this in more detail. Okay, so let's come back to what we were discussing, and we were discussing about the n particle distinguishable case.